software. So maybe some of you already installed the MATLAB software. See, in the MATLAB, they have few windows. This is a current folder, workspace. This is where your, let's say you put here, y equal to 6, equal to 3. When you enter, this MATLAB will save your output data or your input data inside this workspace. This is your parameter that being used. They will save in this workspace. And then we have another Windows editor. This is window editor. You can write your own code over here. Let's say you write CLC. Sorry. CLC, this one to clear CLC and CLC to clear the command window. This is editor window. This is command window. You can save this editor. Let's say CLC, CLEAR, and then you put y equal to 1 plus 1. Okay. Then you put this one, we call it semicolon. Semicolon just to silence the the output in this command window lah. Let's say you just type this one, you put semicolon, you cannot see the answer y plus 1 equal to 1. If you didn't put the semicolon, it will show the output data. Let's say y equal 1 plus 1. When you enter, they will show you the answer, the output. If you use semicolon, it will save your outputs inside this workspace, but not in the command window. This command window, everything you run, it will show it here, except the equation or the parameter that you put semicolon at the back of that particular equation. When you put semicolon, that means don't show this result on the command window. Okay. This is how you save your file. Editor. In editor, you can copy, save everything. Say load curve. And this is a program that I developed. So I use clear. This clear just to clear this command window. CLC, clear command window. This CLC, clear command window. This clear to clear this workspace parameter. So you want to clear all the parameter that has been used in the computer memory. Okay, for the MATLAB, you just type clear. So I just put CLC clear this data. When I write this data, you can actually click F9, Control F9, and then this program will run automatically for the selected area. Let's say I want to run this code. Clear CLC and data, I just put F9, and then this program will run until this point, from CLC until this data. This data is our load data. Okay, this data, right? So this data will be arranged in terms of matrix. MATLAB come from the mathematical matrix, matrix laboratory. So they will arrange this number in matrix. Okay, this one matrix. So this data, first column is the start time, end time. From 0 o'clock to 2 o'clock is this much of power. So it will arrange in terms of matrix, this matrix. Okay. So for the power, so now I want to assign this actually this is our data, and then this power data actually I want to assign. You can do the same. You can type, and then you just select this one. You just run this particular highlighted function. You just go here, Control F9. Where is it called? I just use Control F9. It will run this particular row. So now I have another matrix, another data. Power is equal to all, this one colon, that means all items in all all rows for the item in column 3. All rows, this have what? Row number 1, row number 2, number 3, number 4, number 5, and number 6. This one, this semicolon is to differentiate between row. Okay, this row number 1, row number 2, row number 3, row number 5, and this row number 6 actually. This semicolon is to differentiate the rows because I don't want to put like this. It become longer, so I just actually is you can do like this. They have many rows, but you also can do this like this. Actually, it's the same. This semicolon to differentiate between one rows to another rows. Okay, okay. Let's say you do this, do like this. Also, it will give you the same rows. This power, I just to get this data from the previous data, I just to take this data power, right, at column number 3, all rows, all the rows, row number 1, row number 2, row number 3. I want to take all the data from all rows, but all the data in column 3, this column 3. Then I get this one. That's how we read this program. And the rest also the same. This dt equal to data all rows in column number 2, minus data all rows in column number 1. That means I want to get the duration. To get the duration, I just minus this value with this value. 2 minus 0 will get the duration. So that I can calculate the total power generated for these 2 hours. Okay. And then the rest is our equation. This power generated equal to power times durations. Okay. Total power is sum of this one. You have to calculate for every hours from 0 o'clock to 24 o'clock, 24 hours, right? So you have to calculate all, and then you just sum all the power generated, and then you will get the answer. So this is for the lab number 1. For lab number 2, where's lab number 2? So lab number 2, the equation. Okay, wait. So to calculate inductance, right? Let's say this one. Okay, this is lab number 2. That I give as an example for you. Okay, this program to calculate. Then when we run this program, actually this is the equation that we learn in our class. GMD equal to this value, the cube root of D12, D23, and D13. Can you see this one, or you cannot see it? Too small. Huh?
Too small.
Too small. Wait. Wait. How to do this? It's okay. Okay.
Yes.
Okay. So this one just to clear the workspace. This one to clear the memory of MATLAB. This one too, I declare. So user can insert the value of D12. Okay. So please insert distance between D12. Let's say for 3 phase. 3 phase like this. We have 3 phase, right? We have 3 phase like this. We have 3 phase transmission line like this. D12, I ask user to enter the distance between D12, D23, and D13. Okay, so so I put this programming language. I declare D12 as an input so that user can insert the value of D12, D23, and D13, and then insert the value of radius. The rest is our equation, EPS. This is actually epsilon naught. This one to calculate the capacitance. Okay. So GMD, geometry mean distance. GMD is equal to square roots of D12, D23, and D24. This is the equation to calculate GMD. To calculate inductance, we use this equation, same as what we have learned in the class. Okay. So I just put this one. And then to calculate L per kilometer, I just times 1000. Okay, this for inductance. For capacitance also same. Use the equation given in the slide. Log, you can log. Okay. And this D12 to 3 to 4. This one is a cube root of this value. You will get the C per meter and then just times 1000 to get C per kilometer. Okay. Let's say I try to run this program. Okay, this is my program. Now I run this. Please enter please enter the distance between D12. So let's say 1 meter. B23 1 meter. I just put 1 meter all. Our radius 0.02 meter, and then it will calculate inductance and capacitance for the transmission line. Okay, this is for single circuit, three-phase single circuit. You can use this, the example that I use. But this is for one case. Let's say you have several case, several arrangement. You can play around with these equations, this programming. Okay, what happened when the transmission line is arranged a bit of far from each other? Let's say this one for 1 meter. Let's say if you arrange the transmission lines 2 meters apart between each other, what happened to the value of inductance and capacitance? Then you can do the analysis. We can see the effect of the length or the distance between the cable towards the inductance and capacitance values. Okay, don't just put one value. If you just run for one value, then you cannot see, you cannot analyze the impacts of the distance towards the inductance and capacitance values. Okay. Okay. Anyone else? And to ask about the lab?
Sir,
Yeah.
graf lab 2 tu macam mana? Tak ada?
Graph lab 2.
Yes.
Lab 2, based on this data, okay, let's say, which one, right? Okay. When you run, you have to create a table lah. Okay, let's say, wait lah, this one. Case study 1. Hi. Allah, hi. Wait. Let's see this one. This one. Okay. This is our program to calculate L and C for this type of transmission line, three-phase transmission line, inductance and capacitance. So case study 1, case 1, case 1, case 2, 3, 4, 3, 4. So you have to add more data lah. This D12, D23, D31, 1, 1, 1, 2, 2, 2, just to see what is the effect of this one. Maybe 2 is quite far lah. Maybe 1 point. This one 1.5, 1.5. This one until what? Until 3 is up to you lah. 3 or 4 or 5. So by running the program towards this case, you will get data, right? You will get L and C. This one L and this one C. So from this table, you can see what is the effect of distance towards L and C. This one results. Okay. Either you want to plot the graph or not, is up to you lah. Okay, so this one effect of distance. Another effect you can do is by using different cable size. R equal to 2 cm, and then you increase R to equal to 4 cm, 6 cm, and so on. So what is the effect of radius in terms of L and C? So you have another result. Okay, by using the same program, you can analyze the impact of this one. Impact of one impact of displacement or distance between cable or conductor. Two, effect of radius. Okay, so you have several data. This one table, this one table 2. So you have two results, and then you can analyze that. So finally you know that, oh, when the distance increases, the value of L also increases. Maybe when the radius increase, the L value also increase or decrease. It's up to you. When you do the analysis, you will find out what is the effect of this distance and radius towards L and C values. Okay. Transmission line conductor. Okay. For sure, they have the voltage difference between transmission line. This transmission line, they have high voltage, usually high voltage, and then this is the ground. Because these 2 points have differences in voltage, it will will have some effect. We call as a capacitance effect. Okay, we have capacitance value. This capacitance value is given by this equation. Actually, C equal to number of charge. Charge is the charge. Current is the moving charge. This transmission line bring the charge, right? Charge jumping from one position to another position. That creates the current flow. Charge jumping from here to here, and then create currents. This current produce the power lah, bring the power lah. So this capacitance actually equal to this charge on this cable over voltage difference between this point to the ground. Okay, this point to the ground. This is how we calculate capacitance. Number of charge divided by voltage difference between 2 points will give the capacitance value. Okay, this given by this equation. Usually this C is affected by these factors: conductor size, spacing, and heights above the ground. Okay, so we will see how to calculate the C. So first, because we want to know the C. So what we have to know? We have to know this charge, how many charge that being carried out by these cables, and then what is the voltage difference between these two points. Okay, so we have to know this V between 2 points. So to get the V between 2 points, we have to differentiate this equation and so on. I just skip this one. Okay, this one because Sir Omar already create the video for this, so you just see that one. So actually we have to find V voltage between these 2 points. Okay, 2 points. So by knowing the voltage between two points, and then we will finally can calculate the capacitance effect between these 2 points, point 1 and point 2 is given by this equation. Okay. So actually, this is not what we want. This is capacitance between transmission line and the ground. Actually, what we want is transmission line, capacitance between lines and to the neutral point between these 2 points. So that's why in your slide or in your notes, okay, this equation is, I just move quite fast because you can watch the video that Sir Omar already published in our column. Okay, so this V capacitance between line 1 to 2. This is not what we want. What we want is capacitance between live to neutral or C to neutral. That's why what we get C12, actually we have to convert it to the capacitance to neutral. This is what we will use in our modeling, because in the transmission line modeling, this is our transmission line, right? This transmission line model, we have resistance. We already calculate resistance. And then this is JSL, this is inductance. And then we have to model this transmission line with this pi model to calculate this C over 2, this C over 2. This is our C. We want to know what is the C for this transmission line. That means C to neutral. This is C to neutral. This C to neutral is given by this equation. Okay, so C equal to 2 pi epsilon naught over ln d over r and farad per meter. This is the general equation for the capacitance. As what's happened to the L before this D actually can be replaced by GMD. This R can be replaced by GMR for three-phase double circuit, this one, or three-phase single circuit. This one is for single phase. From single phase, okay, I just summarize what you may learn from the video that has been posted by Sir Omar. Okay, let's say this one. I just write the summary. For capacitance. So capacitance. For the capacitance, we have single phase. We have single phase. Capacitance is given by C equal to 2 pi epsilon naught over ln d over r. This one farad per meter. Okay. For three phase, single circuit, we have C 2 pi epsilon naught over ln GMD over GMR. This R lah, okay, farad per meter. But for three phase double circuit, from this equation, okay, I just replace this R with GMR. GMR. Okay. These three-phase single circuits can be used for three-phase double circuit. So we have the same equation, 2 pi epsilon naught over ln GMD over GMR, farad per meter. So what is the differences between this equation and this equation? Actually, it doesn't have difference. The same equation, but the difference is inside this one. GMD for three phase, for symmetrical line, GMD equal to D. For unsymmetrical, you have to calculate GMD for symmetrical, same as the previous one. You have to calculate D12, D23, and D13. Same as the inductor. This GMD. GMR for solid conductor, GMR equal to same R exponent minus, sorry, for the capacitor it's not GMR, it's R, sorry. It's not GMR, this one R. Okay, R, this one also R. Okay, this R for solid conductor, but for the three-phase double circuit is GMR lah, GMR. So we will see, okay. So we will see based on that one. Wait. Okay. This is the three-phase double circuit transmission line. How to calculate inductance? You see, this inductance is almost similar to the three-phase. This capacitance is similar to the three-phase single circuit capacitance. The difference only this one. GMD same as GMD in inductance. Okay, this GMR for two-phase single circuit. Actually, this value. What is the difference between GMRL and GMRC? GMRL, just now we learned for the inductance. This one for the inductance. GMRC is okay. I just give you the equation first, then we will try to solve the examples. So this GMRC, the difference is only this one. GMRL, we use square root 3 of DSA, DSB, DSC. But now we replace this DS with R. Okay. For the capacitance, we didn't use DS, we use R. You see, inside this one, all the same numbers, same things, and this except DS is being replaced by R. This DS replaced by R, DSB replaced by RB and RC. So this one also same as previous slide, like same as inductance. Except this R replacing the value of DS. Just now for the inductance, we see this DSA. So inside this one also DS, okay, DS, DA1, DA2. Now we replace this DS with DS bundle with R. That's only the difference between the capacitance and inductance. Okay. When you know how to calculate the inductance, basically you can easily calculate the capacitance. Okay. So maybe for the details, you can see this slide. So because we don't have much time, I want to solve one example. Try to solve one example for you. So let's say this one. How to calculate capacitance for this one? This is that one. This is single circuit. Okay. Single circuit 2 wire. We have 2 wires. Transmission line consists of aluminium conductor diameter. This is diameter. So diameter is 50 mm. The two conductors are placed 1.8 meter apart. Okay, this one 1.8 meters. And then the tension line's length is equal to 25 kilometers. And the temperature of the conductor is 20 degrees Celsius. Calculate capacitance per kilometer of this transmission line. So C per 1 kilometer. And then C for capacitance of this transmission line. C for 25 kilometers. This is the question. Find the capacitance per kilometer and then find the capacitance of this transmission line. This transmission line have the length of 25. So we have to times 25. Okay. So how to solve this question? Okay. Okay. Okay, this is the question how that we can use to calculate the capacitance for the transmission line. Okay, single phase, 3 phase use the same equation. Okay. So now we have this data. C is given by C per meter, per 1 meter equal to 2 pi epsilon naught over ln D over R. This one and farad per meter. Okay. So what we have to know is to know this one 2 pi epsilon naught. Epsilon naught is a what we call it? What is a epsilon naught? Permittivity, I think. Permittivity of the space. So where's the value of Permittivity. Okay, this one. Permittivity of free space, epsilon naught. This is value. So actually, you don't have to remember all these numbers. Inside your calculator, they have these numbers. You can call this number by using your calculator. Okay, the preset value. So this one. So how to calculate? Okay. So this permittivity of the free space. This ln d is distance between these two cable, which is 1.8 meters apart. R is radius. So C for capacitance per meter is equal to 2 times pi times 8.85 times 10 minus 10. Minus 12 farad per meter. It's 12 farad per meter. This value divide by ln D is 1.8 meters over R. R is 25 millimeter. 25 times 10 minus 3 millimeters. This is farad per meter. So you will get the answer for this example. Okay. 2 times pi times 8.85 exponent minus 12 divided by ln 1.8 divided by 25 exponent minus 3. You will get this value 13.0022 times 10 minus 12 farad per meter. So C per 1 kilometers, 1 kilometer just 1000 times this value. Equal to 13. 13.0022 times 10 minus 9 farad per kilometer. Okay. This is the value for the capacitance per kilometer. Okay. To get C for the 25 kilometers, C for 25 km equal to 25 times 13.0022 times 10 minus 9. Then you will get 0.32. 0.3251 microfarad per 25 kilometers. Okay. So just this one. 25 microfarad for 25 kilometers. Okay. And this is the value for the capacitance. This value for the capacitance for 25 kilometers. Okay. This question, this exercise, this may be exercise 1. Okay. So, do you get the same answer or not? This one for the single phase transmission line. Same goes to the 3-phase. This one also can be used to calculate the 3-phase symmetrical arrangement. Okay. There's a 3-phase line have this arrangement. Okay. Find the capacitance to neutral in microfarad. How to find the capacitance for this transmission line? So for this transmission line, let's say this one. Okay. So we have this arrangement. Transpose line. This is the cross-sectional area. This is the types of the conductor. Spacing 11 meters. This one 11 meters. Then the diameter is this value. So go back to our equation. C for the three-phase of circuit is given by 2 pi epsilon naught over ln GMD over R. Is farad per meter. This is equation. Okay. So what is GMD? This is difference distance. This 11 meters, and then this 22 meters. So we have to find GMD. Geometric mean distance between these three cables. So GMD is equal to this value. 11, 11, 22. This is how we calculate GMD. And then the radius R equal to diameter 3.625 over 2 times 10 minus 2 meters. Okay. So by knowing these two values, we can straightforward calculate. We can straight through point, and we can calculate the capacitance easily lah, by knowing the value of GMD and R. Okay. So in this case, GMD is equal to 13.85 8591 meters. Radius 3.625 divided by 1.8125 times 10 minus 2 meters. Okay. So by using these two values, we can calculate the capacitance for this transpose transmission line. Okay, this transpose, right? So this arrangement we have to transpose so that we can balance the value of C between phase A, phase B, and phase C. Okay. So C equal to 2 times pi times 8.85 times 10 power of minus 12 farad per meter over ln what's value? 13.85. 1 over this value, 1.8125. 5. Okay, so we will get the value of capacitance per meter.
Apa ni nak? Saya pusing ni.
Eight point 375 2 times 10 minus 12 farad per meter. So C per 1 kilometer. Why usually we ask for 1 kilometer? Usually in the data sheet from the manufacturer, they will give resistance per kilometer. Capacitance we have to calculate depending on our configuration. So we also have to follow that resistance per 1 kilometer. Capacitance also we have to find in terms of kilometers so that we can use these two values to represent impedance of the transmission lines. Impedance Z equal to R plus JSL C, represented by C per kilometer. So that when we want to model our transmission line, we know that R and S, L per kilometer and C per kilometer is this value lah. So we can time how long of our transmission line to represent this by these parameters. We find R per kilometer, SL per meter and C per kilometer. We times the length of transmission line, let's say 120 kilometers. Then this is our model of transmission line. Okay, our values for the transmission line model. So C 1 kilometer, we just time 1000 times this value times C per meter. So we will get a same number times 10 minus 9 farad per kilometer. And this is value. Okay, this is a capacitance per kilometer for this example. So this example, we already solved this one. What time now? 4. Already 4 o'clock. So I think I just stop it here. Maybe maybe I will